Hi, everyone. This week, part of what we're going to go over is kind of a detour, but kind of not, because the kind of data that you learn how to analyze in this chapter is very common. Every time I teach Psychology 3017/4017, there always ends up being at least two or three people who end up using one of these kinds of tests. But it is a departure from what we usually go over because as you'll learn in the last chapter, which is the next chapter, you'll learn that basically everything in this class has been just one form or another of the same general model. And that's true really for virtually everything we've learned in the class, but this is one of the exceptions. This is not part of the general linear model. We'll be learning about the chi-square test of independence and Fisher's exact test, both of which are used on the same kind of data and used under different circumstances. So you'd need to use one of these tests when you're looking at frequency counts for different categories. So right here in this data, we have two variables. We have, I'll say, sex. I've talked before about how, strictly speaking, there are people who don't fit cleanly into a male or female category. However, unless you're specifically going out to study, non-binary people and whatnot, you're probably not going to end up with enough people in the category to do a statistical analysis. For the purpose of the data on hand, you'll usually have a binary male or female. But anyway, we have one factor, which is gender. It has two levels, male and female. And we have voting preference, which has three levels, Republican, Democrat, and Independent. And just like with gender, we're kind of pretending that these are the only categories. There are people who might not consider themselves to be in any of these parties. I guess independent might be kind of a catch-all for libertarians and socialists and whatnot. But anyway, what we have here is we've got two categorical variables, meaning you can be in one level of the category or a different level of the category. You can't be in between. There's no gray areas, no gradations. You have to be either a Republican, Democrat, or Independent, and you have to be either male or female, and we're just counting up how many people fall into each category. So you can't do a t-test because, if I wanted to do, are men more likely to be Republican than Democrat, there's 200 men in this category and there's 150 men in this category. There's no mean, there's no standard deviation because this frequency count is it's a dependent variable, but it's not a continuous variable. It's just one number. It's a count of how many people are in the category. See, with a t-test, if you had height, who's taller, Republican men or Democrat men, then you could go have a sample of 200 men that are Republican, 200 men that are Democrat, measure each of their heights, get a mean, a standard deviation. But this is not that situation at all. We just have how many people fall into which category. So to test this, we would do a chi-square test of independence. And what a chi-square test of independence is doing is it's basically asking, is there some sort of over-representation or under-representation in any of these categories? So we have the column totals, the total number of Republican, Democrat, and Independents when you ignore male versus female. And we have row totals, the total amount of men and women in the sample when you ignore Republican, Democrat, and Independent. So you can take these column totals and these row totals and say how many people you would expect to see in each category if it was completely proportional to the column totals and the row totals. If like being male doesn't affect the probability of being Republican, Democrat, or Independent, or if being independent doesn't affect the probability of you being male or female, then you would expect a certain amount of people to fall into each category. And that's what a chi-square test of independence is testing is, are you seeing that kind of dependence? Are you seeing overrepresentation in some categories or underrepresentation in other categories? And the logic here should be very familiar. We start with a null hypothesis, and the null hypothesis is there is no association between gender and voting preference. In other words, gender and voting preference are independent. Knowing what gender someone is doesn't tell you anything about their voting preference, and knowing their voting preference doesn't tell you anything about their gender. That's the null hypothesis. So basically, just like with any statistical test, the null hypothesis is, suppose I'm wrong and there's really no relationship between these two variables, gender and voting preference. If I'm wrong, is there enough evidence to the contrary to prove that that supposition is incorrect? Like, if can I make the assumption that I'm wrong, but then show that if I assume I'm wrong, then the data are too improbable under that assumption? It's the same logic as before, null hypothesis significance testing. We're starting with the null hypothesis. You have to have some hypothesis in order to be able to tabulate how probable your results are. And if your results are too improbable under the assumption of the null hypothesis, then you can say, well, the null hypothesis must not be true. So I'm going to talk a little bit about the math and how to get these numbers, but big picture is more what I'm concerned about. So you take your observed frequencies, that's the amount of people who actually fell into each category in your data, in your sample, and you calculate the expected frequencies. And I say expected because it's what you would expect if the null hypothesis is true. So if voting preference really is independent of gender, then you would expect to see 180 male Republicans. There actually was 200 male Republicans in the real sample, but if the null hypothesis is true, there would be about 180. Remember, the null hypothesis is never like 100%, like you will see clear evidence of the null hypothesis in your sample every time you collect data. You'll see slight variations. You'll see slightly more Republican men than you would expect if the null hypothesis is true. You'd see slightly less. So 20 is not that big of a discrepancy. You know, the difference between 200 actual and 180 you'd expect to see with the null hypothesis. That's what all these numbers represent in this table down here. We would expect to see 180 male Democrats if the null hypothesis was true. There was actually 150. So we would expect to see slightly more if the two factors are really independent, so on and so forth. So we just basically have, this is the real data up here, and then we use math to say, this is the data you would expect to see if the null hypothesis were true. And the formula for calculating that, I'm not going to make you calculate it by hand. Computer, I don't think there's even a lab assignment that has you doing this, but just so you know, if you were to calculate this by hand, this is how you do it. So for each cell, there's 6 cells in the data. There's male Republican, male Democrat, male independent, female Republican, female Democrat, and female independent. For each cell, you take the row total times the column total. You take the product of those two and you divide it by the total amount of data overall. So you start with male Republicans. The column total is 450. That's Republicans disregarding male versus female. The row total is 400. That's the amount of men disregarding voting preference. So 450 times 400 divided by 1,000. There's 1,000 people in the data overall. When you crunch those numbers, you get 180. And you just apply that formula for each cell in the data. And you'd end, if you're going like I would from left to right, top to bottom, the last one you'd do would be women who are independent women. You'd do the column total, which is 100. There's 100 independents in the sample, disregarding male versus female. So it's 100 times 600. That's the row total for all women, disregarding voting preference. So 100 times 600 divided by 1,000, that gives you 60. That's how many people you'd expect to see in your data if the null hypothesis is true. Next, we need the discrepancy. So I already noted, once you have the amount of people in each category you would expect to see if the null hypothesis is true, now you need to know what's the distance, how far away are these two, the observed actual frequencies and the frequencies you'd expect to see if the null hypothesis is true. Now, you don't just take the raw differences, like there are in fact 200 Republican men, but you'd only expect to see 180, so that's a 20-person difference. You don't go to each cell and just do the raw difference like that. You end up with a sort of corrected, a number that is more standardized. I'll just say it that way. So it's not the raw numbers, not the raw differences. It's actually the raw differences squared divided by the expected differences. Now, I'm not going to make you do the math. If you ever do a chi-square test or a Fisher's exact test, I just want you to know the theory behind where these numbers are coming from. These numbers in this last cell represent the discrepancies. They're just not the raw discrepancies. So for Republican men, there's 200 Republican men, but you'd expect to only see 180 Republican men. So that's a difference of 20. So it would be 20 squared divided by 180, because that's how many Republican men you would expect to see. That ends up being 2.22 ad infinitum. With the Democrat men, you observed 150 Democrat men. You'd expect to see 180. That's a difference of 30. So it's 30 squared divided by 180, and you get 5. So all these numbers in this last cell just represent kind of a standardized difference between what you actually have in your data and what you would expect to see in your data if the null hypothesis is true. The chi-square statistic, that's the lowercase Greek letter right here, chi, and it is squared. The chi-square statistic is just the sum of all these discrepancies. So you see 2.22 plus 5 plus 2.5. That's these numbers right here, 2.22 plus 5 plus 2.5 plus so on and so forth, ending with 1.66 ad infinitum. That's the last number here. You end up with a chi-square value equal to 16.2. So 16.2 is sort of the overall, if you sum up, add together all the discrepancies over each category. That's our chi-square test statistic. That's what we're going to put on a distribution and calculate, like, what's the area under the curve? What's the probability of seeing a discrepancy this big or bigger when you assume the null hypothesis? It's analogous to your t-value, your f value. It's a test statistic, just like those. The chi-square distribution has a parameter called degrees of freedom, and it is equal to the number of rows minus 1 and the number of columns minus 1. In our case, that's 2 minus 1 times 3 minus 1, which equals 2. So chi-square with 2 degrees of freedom equals 16.2. And the computer does this next part for you, but you tell the computer, hey, if you take a chi-square distribution with 2 degrees of freedom and you have a 16.2 or higher, or a 16.2 and lower, what's the probability of getting something that high or higher or that low and lower? Less than a 1% chance. I mean, 16.2 is a very large test statistic. So you'd end up rejecting the null hypothesis. You'd end up saying there is some sort of association between gender and voting preference. There's some overrepresentation or underrepresentation in at least one of these categories. Afterwards, after you've rejected the null hypothesis, Sometimes it'll be clear where the source of underrepresentation or overrepresentation is coming from in your data. With this data, it's not as clear. So what you would want to do is you'd want to analyze there's something called standardized residuals, which would give you a good hint into which one of these cells is really contributing the most to your ability to reject the null hypothesis. I'm not going to get into that right now. Maybe in subsequent times when I teach this class, I might get into that a little more. I'm going to spare y'all this time. So that's the chi-square test of independence. The chi-square test of independence is like any statistical test. It's making assumptions. Namely, it's assuming that the sum of the discrepancies between what you actually have and what you would expect to have in your categories, these standardized values that you're adding up, we're assuming that these, if you were to keep taking samples over and over again and calculating these discrepancies, summing them up, you would have a distribution like a chi-square with this many degrees of freedom. Basically, every time you have an F distribution or a T distribution or a chi-square distribution, you're assuming that that's an appropriate way of calculating the probability of your data. Usually that's a fairly safe assumption. I've talked a little bit about when you violate the assumption of a test, you might want to use a different test. You might want to use a bootstrapping sample if you feel like you probably violated the assumptions of your test too much. One of the biggest violations you see the most with this kind of data, with frequency counts, is when you don't have enough frequency counts in the categories. A good rule of thumb is if one of your categories has less than 5 counts in it, so this category right here, then the data, the discrepancies, the sum of the discrepancies probably don't follow a chi-square distribution. So you'd want to use a different test. And so I made up this data just to illustrate a point. So these numbers are much lower. You got 12, 6, 2, and 7. This data with hundreds of data points and at least 50 frequency counts, not data points, frequency counts. You have a lot more data here. So the chi-square distribution assumption is probably more plausible. With such small numbers here, that assumption of a chi-square distribution is less plausible. And I made up these numbers, but the situation is not made up. So there was a while back, there was a measles outbreak in Disney World, which is unfortunate because we thought we had measles eradicated. But nonetheless, you have a lot of people from a lot of different parts of the world hanging out at a theme park. If somehow a measles virus did break out there, then it would get translated to highly contagious disease. The reason it got my attention, though, is because a lot of people who are anti-vaccine, and this is before COVID, being anti-vaccine meant something pretty different back then. The dialogue about vaccines has changed a lot, but back then, it wasn't really a political issue. People from all across the political spectrum had problems with vaccines. They were very rare, but they did exist, and it wasn't really a political thing. But what they pointed out was that some people who had gotten the vaccine still contracted measles. And some people who did not get the vaccine were probably exposed to the virus, but still didn't contract the virus or, show symptoms or anything like that. And that's plausible because viruses don't necessarily infect everyone that's exposed to them, and vaccines are not 100% effective. They have to be effective to some degree. They have to be better than nothing in order to get approved. And most vaccines, especially the childhood vaccines like these, are very effective. The seasonal flu vaccine can sometimes be like, yeah, it's better than nothing, but it's still not like, it's far from foolproof. But the measles, mumps, rubella vaccine is pretty effective. And but pretty effective doesn't mean foolproof. So if you got vaccinated against measles, you could still get measles if you're exposed. It's a lot better to have the vaccine than not. So to actually get to that question, you'd want to show, like, if someone sees this data and says, oh, well, it looks like the vaccine didn't help, you'd say, well, the amount of people who are vaccinated and have no measles are far more numerous than the people who got vaccinated and have measles, compared to when you look at people who are unvaccinated, it's about 50-50. It's virtually the same, 6 and 7. So people with the vaccine and no measles are overrepresented in this category. And among people who are not vaccinated, there's pretty much an independent, like having measles or not having measles doesn't really make a difference. You could fall randomly in either of these categories if you're not vaccinated. So this guy, Ronald Fisher, came up with a method for calculating if you have small data like this. He doesn't do a distribution where you ask, like, let's do a null hypothesis and then let's calculate the probability of getting my data or more extreme data, and if that probability is less than blah, blah, blah. He figured out a way to just calculate the probability itself without having to do all this distribution stuff. And I'm not going to go over the math, but you can go to websites, you can use a statistical program, you input your frequency counts, and it'll give you a p-value. And the interesting thing about a Fisher's exact test is when you report your statistical tests in a paper, oftentimes you have to say, my test statistic in italics, and then in parentheses is the degrees of freedom equals, and this is what the test statistic equals. And then you say, p less than whatever. With Fisher's exact tests, you just get a p-value at the end. There's no test statistic because there's no distribution. It's just, this is the probability of seeing this much of a discrepancy between what you'd expect if having measles or not having measles and being vaccinated or not vaccinated had nothing to do with each other. If that were the case, then the probability of seeing data this lopsided is less than 5%. And that's just all there is to it. There's no distribution. All right, that's it for that. And I'll soon get started on the very last video of the course. Y'all have a great one. Figure out how to get this to stop recording. Here we go. Bye.